Hey, my name is Nolan Polino,
And I'm Andrew Smith.
and this is our ONR project on implementing a stateful packet filter using a P4 programmable switch. A little bit of what I'm going to go over today is the introduction and the background of this project, the objectives of this project, the solutions we implemented, and the conclusion of our work. The data plane is a structured pipeline that processes a stream of bits as they move through a switch, and P4 is a programmable language that describes the behavior of the data plane, providing the programmer an unprecedented amount of control. Stateful packet filters examine every packet passing through a switch, maintaining a log of various connections and therefore improving speed. And this data is leveraged to enhance the precision of filtering decisions.
So the objective of our project was to implement a stateful packet filter on the Tofino P4 programmable Ethernet switches. The packet filter was developed to interact with both TCP and ICMP. The code is initially written on a BMV2 software switch, and then we migrated it to be compatible with the Tofino chipset on the hardware switches. And the purpose of this project was to demonstrate P4 suitability in high-speed stateful traffic filtering applications.
All right, so for our implemented solution, I'm going to quickly cover the topology of our environment. We have two PCs on the network, and they are both in the 10.0.0 network with a 24 subset. PC1 is used as the management interface for the Tofino switch, and that is where we SSH it into the root of the switch. The goal of this environment was to allow connections to be only initiated from PC1 to PC2 at the level of TCP and ICMP protocols.
So, as another part of our implemented solutions, the project relied heavily on the construct of registers, which are intrinsic to the P4 language. And registers are used within P4 to save arbitrary data, and multiple packets that come through the pipeline can access or modify registered data. We use them here to store and access the ICMP identifier field of packets, for example. And below we see the overview of what a register looks like, both the ICMP and the TCP. The ICMP is stored at the hash index. The index is the hashed value, and then the actual value that is stored there is the ICMP flow identifier. And with TCP, it's a similar thing. At the hash index, the TCP flow identifier is stored. And as to speak to hashes, a hash function maps any given input values to an output value of fixed length, which is perfect for cases where we need to create indexes. In P4, we specify the hashing algorithm, which is CRC16, then initialize the variable that the hash will be stored in. Subsequently, the hash will be used to access the register entry corresponding to the flow we are monitoring. So you see in the visual down here, the first line signifies what hash algorithm we're going to be using, and the second line initializes the variable in which the hash will be stored. And that final line there, cell hash, is the variable through which we'll store the hash value. And in the brackets, we have the IPv4 source and destination address, which is the values that will be hashed, creating the unique index where we're going to store our value. This is what an overview of the register may look like. Using the write data execute to put data into the register, and then the read data execute to read data from the register.
So one of the defining principles of our logic in our P4 program are match action tables. They allow a programmer to define actions to be executed on a certain key, and they're specified in the control plane section of our code. The ICMP and TCP policy tables were designed to implement policies for the ICMP and TCP protocols. The key for the tables identify the flow ID, and for example, the ICMP flow ID is a source and destination IP address, whereas with TCP, you would also incorporate ports. If we look at the logic on match action tables, we can see that there are no actions in the policy tables, since no logic needs to be applied from the control plane. When a match occurs, we interpret this as true, the packet matches the policy for the packet, and on no match, as false, the packet does not match the policy, and we drop the packet. The size of the table is 1024, which is the number of entries in the table, i.e. the number of policies we can implement.
The very first thing we do in our apply logic is first check to see if the ICMP or TCP header is valid. If neither the ICMP or the TCP header is valid, then the packet will be implicitly dropped. However, if we have a match, say on the ICMP packet, the first thing we do is check to see the response type. In the code down below, we see an echo request, which is when the response type has a value of 8, then we know that we are receiving an echo request. During this logic, we will create our hash value by passing through our source and destination address, and then at the hashed value to our register, we will write the current identifier of the ICMP header. And then finally, we're going to continue forwarding. If the ICMP packet is an echo reply rather than an echo request, indicated by the value being 0 rather than 8, then instead of writing, we in fact read the value from the register at the hashed value. We're checking for the ICMP ID, and we're checking for a match. So once we read the value and we store it in register data entry variable, then we compare it to the current packet's identifier value of the ICMP ID. If these match, then we continue and we apply and we allow the traffic to go. Otherwise, it will be dropped. As for the TCP apply logic, if the TCP packet is valid and hits on the TCP policy table, then we store the source and destination port at the hash index of the register, similar to the ICMP policy. If the TCP packet does not hit on the TCP policy, then we instead read the value at the hashed index. If the stored source and destination ports match the current packet, then we proceed with forwarding. This means that it's in response to a previous flow, meaning we're going to allow it. Otherwise, if something that isn't explicitly stated in our TCP policy, we will drop the packet. The hash index consists of the source and destination IP addresses and port numbers. Here's an overview of what that TCP logic looks like in P4 code.
So upon completion of our ICMP apply block, we evaluated the performance. So when attempting to initiate a ping from PC1 to PC2, the action is successful. According to the TCP policy and the rules applied in our Python script, this is correct. However, if sending a ping from PC2 to PC1, the packet is dropped and it is not received by PC1. This is because of our implemented policy in the apply block and our forwarding rules. As for evaluating our TCP, when setting up an iPerf server on PC2 and configuring PC1 as the client, it results in a successful connection between the two. However, attempting to initiate PC1 as the server and PC2 as the client leads to a connection refusal. This again is due to the forwarding rules and apply logic in our environment. As a conclusion of our project, we implemented a stateful packet filter on a BMV2 software switch as well as a Tofino hardware switch. Our P4 code successfully demonstrates the packet filter in accordance with environment configuration and forwarding table rules. We also tested our code to allow connections originating from the internal network and the internal network only. And for our future work, we do plan on implementing timeout on stale entries and collision resolving on flows that produce the same hash value. Okay, so I will quickly demonstrate how our ICMP policy works in action. If we attempt to ping PC2 with one packet, we can see that it was successfully received and there is 0% packet loss. On the contrary, if we attempt to ping PC1 from PC2 with one packet, we see that the packet was lost and dropped by the Tofino switch. Examining the logs from this packet, we do see that the header is valid. However, notice here that the ICMP policy is amiss according to the apply logic and the forwarding rules we have set up, so the packet is dropped. In testing TCP, we initialize PC2 as an iPerf server, listing on port 5001. On PC1, we establish an iPerf client connecting to the address 10.0.0.2. And we see a connection with PC2 on port 5001. If we do the opposite and set up PC1 as the server, and we set up PC2 as the client, the connection has failed. So we can see that the Tofino switch correctly recognizes this packet as a TCP packet. However, it misses according to the rules we have set up. so the connection is only one way. Thank you for taking your time to watch our demo, and we appreciate it.